In this lectorial, we'll consider how fisheries were traditionally managed as single stock using maximum sustainable yield. Maximum sustainable yield is based on surplus population models. That is, that using this approach, what we're looking to do is search for the largest fishing mortality that we can take to offset increased population growth. And so if we look at this here, what we're trying to do is we have got fishing mortality here, we have got reproduction of the fish population here, and what we're aiming to do is maintain our population density at this point here, where our mortality from fishing and from natural mortality is just offsetting the rate of reproduction. So maximum sustainable yield is the largest average catch that can be theoretically taken from a species stock over an indefinite period. So in other words, we can continue to harvest fish at that rate and the fish stock will not collapse. And it aims to maintain the population size at the point of maximum growth. So in other words, the population of fish is growing at its greatest, so we are able to harvest fish at the maximum possible rate while still sustaining the population. To understand the concept of maximum sustainable yield, we need to understand logistic population growth. And for those of you who have done Bio 227, this is not a new concept to you. And so this slide here basically shows time on the x-axis. So we've got number of generations a particular organism has been in an environment, and we've got the size of the population on the y-axis. So initially, when an organism turns up in an environment for the first time, resources are not going to be limited, and initially the size of the population is going to very, very rapidly grow under a model of exponential growth. So basically we've got this doubling of population size all the time. Okay, but once the population size reaches a certain point, resources are going to start to become limiting. And what's going to happen is that the rate of growth of this population is eventually going to slow until it actually plateaus at the carrying capacity. And the carrying capacity is the maximum population size that the environment is physically able to sustain based on the availability of resources. So if we look at this logistic growth curve, what we see is that actually the rate at which the population is growing in size most rapidly is actually halfway between 0 and the carrying capacity here. So what we're looking at here is the slope of this line, and the slope of this line, the change in population size over change in time, is actually greatest at this point here, which is at half of the carrying capacity. And so we can look at this a different way. If we differentiated this curve here, so basically we're plotting the slope of this curve against population size, you can see this more clearly, that basically initially our annual population growth is increasing and increasing and increasing as our population doubles and triples and quadruples and what have you, until we get to this maximum sustainable yield, which is half the carrying capacity. And that is the point at which the annual population growth rate, so not the individual population growth rate, but so not the individual growth rate, but the population growth rate is at its greatest. And above this point, or in population size, what happens is that because resources are now becoming extremely limiting, this population growth rate slows. And so this here is an equation that will be familiar to some of you, which is the logistic growth equation. And so this dn dt is just describing the change in population size over change in time. So in other words, population growth rate, and it's equal to the intrinsic rate of growth times the population size. So this is what would be happening under exponential growth if resources were not limiting. And then we need to take into consideration here how far away our population is from the carrying capacity. So what we're doing is subtracting the ratio of where our population is relative to the carrying capacity. Okay, so here it is again. We have our change in population size over change in time. We've got our per capita rate of increase. We've got our population size, and we're taking into consideration how far away we are from the carrying capacity. Okay, and so I guess initially, as we approach the carrying capacity, the rate of growth is going to slow, but is still going to be positive. As we exceed the carrying capacity, what is going to happen is that population size is not sustainable, and our population is going to shrink until it returns to the carrying capacity or below. So historically what we have done is set fishing quotas based on this maximum sustainable yield, which sits at half the carrying capacity. So this seems simple on paper. You know, we know what the carrying capacity is. We look at the population size that is half of that, and we try and maintain our fish stock at that level because that's where it's going to be growing at the greatest rate, and per unit time we can extract the most individuals and maintain a sustainable population size. But this is actually much easier in theory than in practice, because it's actually very hard to obtain a reliable maximum sustainable yield. The other problem is compliance. So although it might be easy to say to fishers, you know, you cannot exceed this level of catch, in practice, it's much harder to enforce that than it is to actually state it. And so what we can have happen is that even though we have set a realistic catch size based on, or a sensible catch size based on maximum sustainable yield, due to non-compliance that can be exceeded, and that can drive our fishery towards collapse. The other major issue with this approach of maximum sustainable yield is that the carrying capacity of the environment varies. So as I said before, carrying capacity is the maximum number of individuals that a population is able to sustain. Now, as we all know, the environment is not unchanging. It changes considerably through time according to, you know, season and temperature and how much resources are available. Sometimes we have good years because there's been lots of rain. Sometimes we have bad years. You know, sometimes there's more nutrients, sometimes there's not. And so actually, if we are extracting a certain number of fish based on this calculation of maximum sustainable yield, if the environment changes, we might find that we are either over extracting fish or we're extracting fewer than we need to actually be sitting at the maximum sustainable yield. Okay, so this is just a little diagram showing this here. So here we have got our population and our population growth rate, and our MSY is going to be half at the carrying capacity. So basically this point in the curve here. But what this slide is showing, or what this picture is showing, is actually the carrying capacity of the population can vary markedly from time point to time point, and this is actually going to influence the maximum sustainable yield. So if we set our maximum sustainable yield when our curve looked like this, and we continued to extract at this rate, but the carrying capacity of the environment shrunk, what we would be doing is considerably over extracting fish, and we might actually drive our population towards extinction. So what are the factors that actually affect the carrying capacity of the environment? Well, there are density independent factors. So as I said before, weather. So whether there are storms, whether there's cold, whether there's periods of drought. There is density independent stressors. So for example, DDT poisoning, that kind of thing. Other factors that affect the carrying capacity are actually density dependent. So the availability of food, space, so if organisms are maintaining territories, denning sites or nest cavities, and density dependent epizootics, so various diseases that depend on how dense the population is. The other problem with maximum sustainable yield is that it also assumes that all individuals are identical, and clearly they are not, and it assumes that there is no immigration and there is no emigration outside of a particular area in which we are setting our catch limit. And it also assumes that co-occurring species can be managed independently of one another. But what we might actually find is that multiple species actually utilise the same resource. So although we might actually be, setting an MSY that seems realistic based on the amount of resource that's available for a particular fish, if it has a competitor that is actually using the same resource and we haven't taken this into consideration, this actually might lead to overharvest of the fish. So what is the history of maximum sustainable yield? Well, the maximum sustainable yield, the idea of this was developed in New Jersey in the 1930s, and it was initially adopted by the International Whaling Commission, the Northwest Atlantic Fisheries Organisation, and several countries. In 1955, the US manoeuvred to have maximum sustainable yield declared the goal of international fisheries management. So you can see that this was very much the cornerstone of fisheries management in the earlier years. In the 1970s, things started to go a bit pear-shaped and people started to ask, well, is maximum sustainable yield really able to deal with real-world complexities? But nevertheless, by 1982, this principle of maximum sustainable yield had been incorporated into the 1982 United Nations Convention for the Law of the Sea. But by 1990s, we were seeing serious problems with collapse of several fisheries that had been managed using maximum sustainable yield, including the northern cod. So this slide here shows the collapse of the Peruvian anchovy fishery. So here we have landings since 1950, and you can see with the maximum sustainable yield approach, we have this major crash here, and it was only after closure of the fishery that recovery was able to occur. So this raises the question, is MSY the be-all and end-all, or is there a better way to manage fisheries? Continue on with the module to find out.